This is section 13.4, conditional probability. So with conditional probability, what happens is the bottom number, the total you have to choose from, is going to change. So let's look at our first problem. We're drawing a single card from a 52 card deck. Find the probability that it's a diamond given it's a red card. Okay, this represents the word given. So on top, you're going to have red diamonds. And on the bottom, you're just going to have reds. So if you pull up your image of a deck of cards, you'll see that half of them are red, so 26 are red. Diamonds are a suit. They are reds, and there are 13. We do need to reduce that. All right, so find the probability the service was good given the meal was dinner. Okay, probability the service was good given the meal was dinner. So on the top, you're going to have good and dinner. And on the bottom, you're going to have the total for dinner. So good and dinner is 18. All the dinner, the total for dinner is going to be 65. So let's flip this over. I'm going to assume they probably want a decimal on this one. Let's do 2 decimal places, 0.28. So again, read the instructions below where you put the answer. They'll be in blue. It'll tell you whether it's a fraction. If you see the word fraction, you're going to leave it as a fraction. If it's a decimal, it'll tell you how many decimal places to round to. All right, let's look at these. The probability it was a heart given it was yellow. So on the top, you're going to have yellow hearts. And on the bottom, you're going to have the total that are yellow. Okay, so that's going to be 1/2. The probability it's pink given it's a smiley face. So on the top, you're going to have pink smiley faces. And on the bottom, you're going to have all your smiley faces. So that's 4. Excuse me. All right, so our next one, probability it's a blue given it's a star. So on the top, you're going to have blue stars. That's 1. Out of all the stars, so 1, 2, 3. Probability it's a star given it's pink. So on the top, we're going to have pink stars, which is 1. And then on the bottom, all the ones that are pink, 1, 2, and 3. No, wait a minute. Right there. Okay. Boom. If a student is selected randomly from those surveyed, find the probability that the student is a Democrat given they preferred candidate A. So probability they are a Democrat given they preferred A. So on the top, you're going to have the combination of 2, Democrat and preferred candidate A, over the total, that preferred candidate A. And let me convert this to a decimal. So let's just, I'm going to do 3 decimal places, not for any particular reason. 0.729. If a student is selected from this group, find the probability that the test is positive given they have mono. So the probability the test is positive given they have mono. So on top, it's a positive test in mono. And on the bottom, it's all the ones that have mono. So 0.60. So we could say that that test is 60% effective in determining if someone actually has mono. This is one of the ones that students miss the most, so I would recommend you don't have to draw the jar out, just make a little chart. All right, so we have 10 blue tokens. We have 5 green and 5 red. So the total we have is going to be 20. All right, so the probability that you select a non-blue token first. Okay, so let's just look at this. We're selecting a non-blue, so we're selecting a red or a green, and this is without replacement. So say we select a green, we pull that out. It's green. But we don't replace them. It's without replacement. So we only have 4 green, and then the total we have in the jar is 19. Now, here's where it comes into play. The second token is non-blue. So how many non-blue tokens do we have now? We have green and red, so that's 9, over the total left in the jar, which is 19. Set this up again. The first, you select a green token, and this is without replacement. So when we pull out 1 green, we're left with 4 green, and the total changes to 19. The probability that the second one is non-green. So non-green would be red and blue. It's going to be 15 over the total in the jar, which is 19. So it's, how it would read is the probability that you select a non-green token after you've selected a green token first. But I would do this little setup here, just write those out and change the composition of the jars. All right, experiment 2 events are given to determine if they are independent or dependent. A penny and a nickel are flipped. We have heads on the penny and tails on the nickel. So if they are independent events, one does not affect the other. Dependent means one does affect the other. So if you flipped a heads on the penny, does that affect what you flip on the nickel? No. They're independent. All right, you have 2 dice, and they say one's red, one's green. I don't know why they distinguish colors, but it's kind of irrelevant. All right, so you have 2 dice. The red shows a 5, and the total is odd. So does what shows up on the 5 affect the total of the 2 dice? It does. So these are dependent events. Okay, so let's just look at this. You may need a little breakdown. You have red and green and the total. So if we roll a 5 on the red, and then if we roll another 5, or even something like a 3 on the other dice, that total is going to be 8, which is not odd, it's even. Okay. So say we roll a 6, 5 plus 6 gives me 11, so that's an odd number. So what's rolled on the red does affect the total. So the red has to be 1, 3, or 5 if the green is an even. Okay, so we have to have an odd and an even. So if we didn't roll a odd number on the red and we had a 6 on the green, then the total would be even. So one does affect the other. It affects the total. So those are dependent events. I believe that's all we have for section 13.4.